Thank you for coming to the presentation. I'll present this work called the SUPERPACK Dishonest majority MPC with constant online communication. And this is from work with Daniel, Vito, Antigone, and Ethan. So let's get started. And if you have any questions, please feel free to stop me. So first, this is the concept of the secure multi-party computation. We assume that there are n servers. They are in the middle here, the P1 to Pn, and we have n clients, C1 to Cn, because we focus on the client-server model. But you don't need to care too much about clients. We are only see them in two slides. And we have a function f, which takes the input this x1 to xn and output y. So the goal of MPC is to securely compute this function f without leaking anything beyond the output y. So the basic setting in the client-server model is like these clients who hold the input will secretly share their input to the computing servers to P1 to Pn, and P1 to Pn will engage in an MPC computation. So ideally, it's like there's an MPC functionality who computes this function and return the result, and they will deliver the result to the clients.
So the clients are the one holding the inputs?
Yes.
Okay. Then what do you mean by like P1 sends X1 to the functionality and so on?
Oh, you can view this X1 as the share received by P1.
Okay.
Yeah.
Thanks.
And the servers does not know any inputs. They only get secret shares.
Mm-hmm.
Yeah. Okay, so our setting is as follows. This function f will be represented as an arithmetic circuit, which consists of addition and multiplication gate. So, and we assume dishonest majority, which means that majority of the servers will be corrupted by an adversary. So specifically, we'll define a constant epsilon, which is in the range of 0 to 1 over 2, and epsilon is the proportion of the honest servers. So in this way, we have epsilon n honest servers, and the rest of the servers are corrupted. We define a parameter t to quantify the number of corrupted servers. Okay, so we assume a malicious adversary who would corrupt at most the t servers and a subset of clients. Okay, so a little bit about our results. This work achieves the constant online communication per multiplication gate among all parties. So the total communication for all the parties is constant. So this is the average cost to compute one multiplication gate. So a little bit intuition about that is like each message they send and receive will be used to compute multiple multiplication gates. That's why we achieve constant communication. Okay, so but computation is not linear to n at all, and we have a flexible choice of epsilon, so we can take any epsilon that is in the range of 0 to 1 over 2, and also the choice of epsilon impacts the communication cost, and the communication decreases as epsilon increases.
So here, when you say constant online communication among all parties, does that mean that all parties sends constant number of field elements?
Yes,
for 1 gig.
Right.
So it's not per client, or not per server, it's all servers.
Yeah, the total communication.
Okay.
Yeah. So our protocol is split.
So hold on, can I continue about that question? So if the circuit has only 1 gate, you are saying in the online phase, most people don't have to talk.
No.
Don't they at least have to receive the result or something? So I don't understand.
No, it's the amortized cost. It needs a fairly large circuit, and also there's another assumption that the circuit has weight larger than k. The k is a parameter we'll define later. So if it is a very narrow circuit, also we cannot achieve this.
Wait, so hold on. So what are all the hidden assumptions you are making? Like this is very confusing because I guess if it's a single gate, you are saying you still need a large amount of communication.
Yeah, if it
Because
is a gate, we cannot achieve this result. We'll assume that a circuit has is at least of width k. The circuit
at
will-
least of what's
will
k?
be
K
widely
doesn't show up in any of these other parameters. What is k?
K will be a parameter I'll define later. It is a packing parameter we use in a pack-Shamir secret sharing.
Is it? I mean, it has to depend on n, right?
Yes. We'll need it to be proportional to n. Yes. So this protocol will be based on pack-Shamir secret sharing. So we hide a bunch of k secrets in one pack-Shamir share and compute based on that. So for each computation, we'll like do a SIMD operation on all of these secrets hidden in one pack-Shamir share. That's how we achieve this amortized like constant cost.
I see.
Yeah.
Also, but how about, is this the first paper that achieves constant online communication for dishonest majority?
No, Vipo has a previous paper. I'll show some comparison. It also achieved constant communication, but it comes with a larger constant.
I see.
Yes. And also there is another trade-off is that Vipo's previous work achieves like constant communication for all the phases. But here, as you can see, the circuit is independent preprocessing actually needs a factor that's linear to n. We only achieve constant online communication for the constant communication for the online phase and circuit dependent.
So you're saying it's asymptotically worse than the previous paper, but for the online, it has better constants.
Yes.
With some trade-off in terms of the offline.
Yeah, right.
I see. And then is the online phase information theoretic?
Yes. This work is also based on like previous MPC protocol is based on OLE and vector OLE, and other parts are information theoretic. Okay. Yeah, as you can see, these are the three phases in our protocol, and for the circuit independent preprocessing, we can also use the technique from previous work to make it constant communication, but we want to achieve more concrete security, so we added some factor that would be linear to the number of parties. Yeah. Okay. So here are the related works. The first category is the Pedrosa and the Spies protocol. They assume all but one corruption, and they are like concretely efficient MPC protocols. But it's not clear how to benefit from the case when actually there is more than one honest parties among these N servers. And the best approach we can think about maybe is to randomly sample a committee of size T+1, because they are the protocol that assume all but one corruption. You randomly sample a committee of size T+1, and you guarantee there is at least one honest party among these T+1 parties. Then you can use this protocol to compute the MPC, then deliver the result to other parties. So we'll do some more concrete comparison with this type of protocol later.
Hold on, maybe I'm confused. So epsilon is the fraction of honest parties. It's not an arbitrary parameter. It has to. It's the fraction of honest parties.
Yes, it's a constant factor.
So I see. So on your previous slide, if you have all but one corruption, it's still not constant. So basically this doesn't hold if it's like all but one party It only holds if at least there's a constant fraction of honest parties. This
Yes, I guess in this work we cannot. In our work we cannot achieve all but one.
Is it know how to get constant online communication if it's all but one?
Sorry.
Is it in the all but one scenario? Is it know how to get constant online communication, or is it possible to get it? Is it?
No, I haven't seen any work that could achieve that.
So you are saying that the previous paper also made the same assumption that constant fraction is honest.
Yeah, right.
I see.
Yeah.
And questions? Why your construction cannot achieve all but one? Because epsilon can be arbitrary.
Yeah, but concretely, we actually need the number of honest parties to be at least 2. Yeah. So there will be a gap there. Yeah, because the number of the values packed in packed secret sharing is approximately half of the number of honest parties. So we need that to be at least 2. Yeah.
So it works for 2. Like even in that case, the epsilon will be 2 over n.
Then yeah, it works for 2. Then there's no advantage. Then it will be probably the same as any like MPC protocol based on Shamir secret sharing. Yeah, there won't be any advantage. If honest party has 2, then we just construct the protocol like dishonest majority protocol based on Shamir secret sharing, and there's no other advantage.
So I think the main advantage is that when epsilon is not that small. Right?
Yeah.
Okay.
But even when epsilon is small and at least 2 honest party, the protocol is still secure.
Yeah,
Yes, it should.
secure, but it's not good.
Right.
But if there's only 1 honest party, then the protocol is insecure.
Then I guess it wouldn't work. Yeah, it's not secure. Yeah. Okay. So there's another protocol by Zippo et al. It also achieves this constant communication per multiplication data, but it comes with a pretty large constant. Okay, and there's another work. It is a multi-party gobbling scheme called Tiny Keys. It also considers to leverage the trust assumption on a variable number of cooperative parties. But it focuses on leveraging this assumption to reduce the gobble label size. Eventually, it also reduced the communication, but it's in a different setting. And it only works for Boolean circuits. And the last one is a work called SUPERPACK. It can be viewed as a predecessor of this work. It is the honest majority MPC with constant online communication. So it's the only difference is the trust assumption. So, and we also use some techniques from the SUPERPACK as well. Okay. So I'll briefly talk about the pack sharing secret sharing. And first, let me define 3 parameters: n, k, and d. N is the number of parties. K is the packing parameter, that is number of secrets we'll pack in the pack sharing. And d is the degree. Okay, so for the pack sharing, I'll denote it in this way. First, we assume that there's a vector v, which is of dimension k, and we denote it as v in a bracket with a subscript d to be a pack sharing. And first, let us define k plus n distinct elements, alpha 1 to alpha k, and the beta 1 to beta n. And this will be used as the evaluation points, and they must be distinct. Okay. Then, similar to what this figure is showing, and we'll construct this sharing scheme. First, on the left-hand side, we have evaluation points alpha 1 to alpha k, and we'll define these evaluation points, the value of these evaluation points to be v1 to vk. That is the secret we want to hide. And on the right-hand side, we'll randomly sample the d minus k plus 1 point evaluations. Then now we have d plus 1 points. It defines the degree d polynomial. Okay, now the polynomial is fixed, but we have the rest of, we know the evaluation of the rest of the points. Then each party pi will learn 1 point evaluation on the right. So pi learns the value of f at I, and that is the texture measuring. And so because any d plus 1 points define this polynomial, then it means any d plus 1 parties can reconstruct it if they behave honestly.
Is there any construction between N, K, P?
K is smaller or equal than D. You mean the relation between it?
Or constraint?
No, it's just that K is smaller or equal than D. Then they're smaller than N. So yeah. Okay.
I guess I don't understand the notation. What is V square bracket subscript D?
Oh, it means a packed Shamir sharing of vector V with degree D. Yeah, and it can be viewed as the degree of the secret sharing or the degree of this polynomial. Yeah.
Another question.
So this notation denotes all the shares, like
Uh,
V square outputs all the shares. Is that what the notation means?
you mean individually for each party?
Yeah, I mean, if you are not going to use this notation, then it's not important.
Yeah, I'm going to use it. It's just it should mean like all these shares jointly.
I see.
Yeah, yeah. Do you have any question? Okay. Okay, so now we have the texture measuring. We are ready to use it to secretly share the Y values in this circuit. And assume that we have a batch of K Y values in the circuit already denoted as a vector V. And since we have texture measuring, do we just directly use it to apply to this V with arbitrary degree D we want? But we are not going to do that because there is an alternative way, and we'll see the benefits later. So here, the D is actually split into two parts. So our protocol never explicitly secretly share V. Instead, we secretly share the lambda and the mu. And this lambda is a random mask, and parties will use this secret sharing scheme to share this lambda. And this mu, if the lambda is random and it is secretly shared, then it's safe to public this mu. So any party can know this mu. And so throughout this protocol, all of the Y values will be shared in this way. So we never have an explicit secret share of V. All the Y values will be shared as a masking representation.
Do you say mu is everyone knows mu, or mu is secret shared?
No, mu is a public information. Anyone can know. But yes.
Okay.
Yeah, but in our protocol, actually, we only need mu to be known by P1.
But I don't understand the notation. It seems like these vectors, the dimensions don't match. What is the dimension of V square bracket sub D? It's not K, right?
But no, this D is not it's not K, it's different. It's larger or equal than K. And if it is used,
I don't understand what's the dimension of each of these vectors?
the dimension is K.
So this V subscript V square bracket subscript D outputs just a length k vector. If you
Oh.
want to have output the share for everybody, shouldn't that be length n?
Wait, could you repeat?
I think this notation is pretty similar to standard just one share or one field element sharing. You're using brackets where, like, if you forgot about the D and everything, if you just used one field element as a secret, traditional secret sharing, you would actually write things down on a whiteboard with brackets around it saying bracket, alpha, bracket, beta, and you add an open constant to it on the side. I think that's
Yeah,
the
yeah.
confusion is here, but this
Oh, I
bracket sub D thing is just a convention for something that is a K element tuple. Of sort. These are essentially a K element tuple on the left is equal to a K element tuple on the right, which is secretly shared. All of them are secretly shared through some bizarre scheme, whatever scheme you want to use, but it's through some scheme, and it's the same kind of notation as in one element sharing.
Right. So yes, for each server, for each party, they only get one field element as a share. Yes.
Yeah, I think I'm going with like it's a blob on the left equals a blob on the right plus something that is open in the public. The same kind of notation you would use if you forgot about like packing or anything like that would be like I'm sharing 7 on the left and then I'm sharing 3 on the right and the open thing is 4. So
Yeah.
it sounds like that's where the confusion is coming from. Is what does this bracket
Yeah,
It means a
Sorry,
lot.
I don't understand the notation because it seems like the vectors, the length don't even match. How can you add them if their length don't match?
They are all okay. So they are firstly that they are all of length k for these vectors.
But like
And,
the
inside.
the inside, yeah.
The inside is not like okay, but the outside, like
It's
after you secret share it. So.
It's length.
Oh yeah.
V and lambda is a length k.
I should define how to do this addition, right? So if you want to do addition between a secret shared element and a public vector, who is also of length k, then they can locally convert it into a pachydermal sharing of dimension k-1. And you can add 2 polynomials just by adding each party, adding their own shares together.
I feel like in a sense, they're
Sorry,
dealing-
it's not clear how you do it. I don't understand this notation.
Really?
Is this notation important?
So like basically what is happening, I think, is that you have like the vector v, which is like a vector of length k, and you have vector lambda, which is also of length k, right? And then on the left hand side, you have the sharing of the vector v, okay, which is being shared with the polynomial of degree d. And then on the right hand side, you also have a sharing of vector lambda, where the sharing is basically like a polynomial of degree d. And basically like to like you like sum like every share plus some like publicly known value. So it's like it's not necessarily just like the degrees like match up or whatever. It's just like you have like on the left hand you have the sharing, and then on the right hand you have the sharing, and then you can like plus mu, where like mu is basically you will just add this value to like every share of the polynomial of degree d.
So mu is a length k vector, and every share shouldn't it be a single field element?
Yeah, can view it as can view all of them as a polynomial. For example, the share of V is a polynomial similar to this case in this figure, and the share of lambda is also a polynomial. You can and each party knows 1 point evaluation. They can just do the addition on the polynomial or subtraction on polynomial by just adding or subtracting their own shares. And if there is for example, a public vector of length k, it can also be interpreted as a polynomial, and they can freely just do addition and subtraction on them.
Like if you put the mu on the left, and just write down mu sub k, mu sub 2, mu sub 1, or whatever in there,
Yeah.
and then you use Lagrange interpolation, you figure out what the things are that you add to the right.
Right. Yeah, they
That's
can.
maybe what you're saying just now.
Yes.
if you picked an example like this and drew it on a whiteboard and stuff on the left, it's the same as in normal secret sharing, except in normal secret sharing, it's almost trivial because your secret's on the y-axis. And therefore you can just add the same thing to all betas. But in here, it's a little trickier because your public thing is now to the left of the axis. But it determines precisely what you add on the right.
Right, yes.
It's almost like the Lagrange Van der Waals matrix or something like that.
Yeah.
You just multiply the mu entries by to get the n other entries that you add.
Yeah, and
It's all public.
right, even if two polynomials are or two shares are of different degree, they can still be spun up or be subtracted from one another. But it's just the result that is the one with higher degree.
So in the next slide, when you add mu is actually add on the plain text V. So later on, when you secret share, essentially is we actually add like mu1, mu2 to each share.
Yeah, well, yeah.
Equivalent to add mu to the.
It's the mu's on the right side, I think.
Uh,
So this, if you had some function here like L of mu, right? You could write that L of mu, and what L of mu does is just deterministically maps things to the right side. It interpolates internally. It's a program just interpolates everything to the left, and then figures out what is, L something of beta 1, L something a polynomial of beta 1, of beta 2, and that everybody knows. So if you tell everybody what mu is, they know exactly what to add to their level.
yeah, right.
And that's what's a little confusing. They're not adding like an individual k entries to mu. They're adding n to an n vector.
I see.
And each one of those n things is something everybody can figure out on their own without talking to anybody. It's written down in stone and just apply it once for all. When you know mu to the left.
Right.
I hope I'm understanding this right. I think that's not like
Yes.
mu gets stacked on top of the alpha. Indices, and then some polynomial gets interpolated, and that gets you a bunch of things, right?
Yes.
And everybody knows what there are. Yeah.
Right, it's not to the case that when you know the vector mu of less k, and this polynomial is completely public.
Sorry, I didn't know that. Is that kind of what you were getting at, or draw a picture?
Yeah, I think so.
Elaine, does that solve your confusion?
I cannot hear the audience, but the way I understand it is everyone computes their share of mu and they add their share to the share of mu to their share of lambda. Is that what you mean?
Yeah, right.
Okay, thank you.
Thank you. Okay, so we will use this like representation of the where values throughout the protocol. And okay, since we are using the pack sharing, another difficulty, another challenge is to how to get around the SPDZ computation and make it work for arbitrary service. So let me take simple example. For example, for the first few layers, we will have these lambdas generated. And when we get to the point of layer I, we have this lambda 6, which the contents in lambda 6 are from different lambdas from previous layers. For example, the first element is the first element of lambda 2. The second element is the second element of lambda 1, and so forth. And how do we make sure that we can do this network routing to make sure the lambda can be generated at the correct slot? So we'll need a protocol to get around this challenge. And we call it a problem of network routing. And there's a very simple trick. It's called secret selection. So previously we have talked about how to do addition and subtraction on pack-sharing sharing because it's additively homomorphic. We can do it. And actually, they can directly compute these two polynomials as well. For example, they have the shares of two polynomials. Each party just locally multiply its share of two secret sharing. And the result is the multiplication of two polynomials. As long as the degree does not exceed n-1, then they can still reconstruct it. So now we need the multiplication here. Assume that we need the lambda beta, whose first slot should be the same as the lambda alpha. So we'll get a unit vector E1, which has the first slot to be 1 and the rest slot to be 0. And by multiplying two polynomial or two packtime sharing, it's equivalent to do element-wise product on these secrets. Then we have this lambda beta, of which the first element equals the first element of lambda alpha. Okay. And we'll use sheet to construct all the lambdas in the preprocessing phase. So first we have a circuit independent preprocessing where parties will generate all the random masks of lambda for each wire. Now first we forget about the group of k wires. We just view each wire as wire j, and it has a mask lambda j. So they'll compute a secret sharing of this vector lambda j such that all the elements are the same, which is lambda j in all the slots. So this is the package sharing. Okay, this will be done in the circuit independent preprocessing. So in the circuit dependent preprocessing, when they know the circuit structure, they know which lambda should go to which pack. Then, for example, here, when they need lambda 4, the first slot is from lambda 2, second slot is from lambda 3, and third slot is from lambda 1. They just use 3 selection vectors to do this, to first select the lambda from the correct position and then do a linear combination. Then they get the shares for lambda 4. Yeah, and you can also take a look at the degrees here. The unit vectors has degree k minus 1 because it's of length k and it's public information. So it only needs to be of degree k minus 1. Basically, all parties can locally reconstruct that polynomial and know their own share. And for other secrets, they are degree m minus k. So if they sum that up, they equals to m minus 1. It does not exceed the maximum degree. But if we want, for example, the lambda 4 to be of lower degree, we'll have to take extra steps to do degree reduction. But it will not be covered here. Okay, so that is a network routing for lambda. And as I mentioned, that all the secrets are split in two parts, the lambda and the mu. So, but this mu, since it's public, it's free to do the network routing. We just let P1 to locally reconstruct this mu and put the correct mu at the correct position. Okay, so now I'm ready to describe our protocol. I first mentioned a simplified version of the online protocol. So we assume that this is overlapping of k multiplication gates. We'll group the computation of them. And for each input wires, it has mu alpha, known by P1, and lambda alpha, secret shared by parties. And it's also same for mu beta and lambda beta. So ideally, it is to take input V alpha and V beta and output their element-wise product, which is V gamma. And so actually, they have this mu's and lambdas, and also the random mask lambda gamma for the output wire. If they correctly compute this vector mu gamma, then it defines the value for the output wires. Okay, so our goal is to compute mu gamma. And I'll split into two boxes. The first box tells us what does P1 know. The rest, the next box tells us what are the secret shares among all parties. Okay, so P1 knows all the mu, and so in the previous layers, P1 could reconstruct all the mu's and put this mu in this correct position and construct mu alpha and mu beta. So the mu's from mu alpha and mu beta come from different packs from the previous layers. Okay, so, and then P1 can distribute these mu's mu alpha and mu beta to all of our other parties in the degree Qmax1. This is the lowest degree because they do not have to capture the secret. And in the pre-processing phase, they also share these values. We have seen this lambda alpha, lambda beta, and lambda gamma before. They are random masks. And additionally, we also need that the last one is a capital gamma. It equals to an element-wise product of lambda alpha, lambda beta, minus lambda gamma. So it is similar to a bigger triple. Yeah. So this is what we want to compute in order to get mu gamma. So parties will compute the right-hand side of this equation. We have seen the multiplication and the addition operations before. The parties just use their local shares to compute this equation and get one share of mu gamma. And then they will reveal this mu gamma to P1. And P1 could reconstruct this mu gamma. Okay. So, and all of these values on the right-hand side are from either from previous pre-processing or distributed by P1 in the online phase. Okay, so let's take a look at the communication cost here. So P1 distributes the shares of mu alpha and mu gamma, mu alpha and mu beta, and it costs 2 ms1 field elements. And after the computation of these parties reveal this mu gamma to P1, it costs another ms1 field elements. So totally it will be 3 multipliers mu ms1 field elements. And in order for all of this computation to be correct and to be secure, we need K approximately to be epsilon n over 2. That is half of the number of honest parties. So if we amortize it, that is, we assume that the circuit is wide enough. So in all computation, they can always group at least the K gates in a pack. Then the average communication cost per gate is 6 over epsilon field elements. Yeah, this is how the constant communication is achieved.
So technically the field size has to be big enough, right? Like bigger than the number of parties, for example.
Oh, yes, yes.
So technically you still have the log n factor here.
Oh, yeah, right. Yeah, that's true. We need a moderately large field in order to get those K plus N distinct evaluation points.
Okay.
And also, because in this work, we want to get malicious security, and we have to use a MAC in the end. And actually, we'll still need a large field. So, but it's true that it's not fair to not include that factor. But I think the collaborators in this work, Daniel, he is trying to do something to get around this factor by using things like RMFE. MFE allows you to have multiple smaller elements in a large field. Yeah, so what I showed is a simplified version of the online protocol. As you can notice here, we need to prepare this capital gamma in the pre-processing phase. And here we need to do a multiplication for random masks, lambda alpha, lambda beta. So actually to compute this multiplication, we have to go through very similar protocol again in the pre-processing phase. But our observation is that we can actually combine these two multiplications just into one step. So instead of like doing this multiplication in the pre-processing and leverage this capital gamma to do multiplication online, we'll combine these two in just one step online. So the actual protocol will be like this. P1 still knows mu alpha and mu beta. And additionally, in the circuit-dependent pre-processing, we have P1 to know lambda alpha minus A and lambda beta minus B. And also from the pre-processing, instead of getting this capital gamma, the parties will directly use the Beaver triple ABC which are used to compute the capital gamma. So this is from circuit independent preprocessing. They'll directly fetch it and use it in the online phase.
How do you generate the packed beaver triples?
We'll use vector LE and OLE. Maybe not to mention vector LE now because that is used to get the MAC. But we'll use OLE to do it, but with some sharing transformation. We have some protocol to switch back and forth between additive shares and packed Shamir shares.
I see.
Yeah.
But that also counts as beaver triples, right?
Yeah.
Okay.
Right.
Thanks.
So I know some group who is studying directly generating packed beaver triple from maybe OLE and also authenticated version from OLE, but I don't think there's any result right now.
I see.
Yeah. Okay, so from circuit dependent preprocessing, the P1 would know lambda alpha minus A and lambda beta minus B. So here it might be misleading because in the circuit dependent preprocessing, P1 doesn't know mu alpha and mu beta, but only the elements on the tail here. Okay, so P1 can compute this V alpha minus A and V beta minus B online. And then it distributes these values just in like the previous case. And then the parties compute a very similar equation. It's very similar to the previous case, but use these newly generated elements to replace the mu alpha and mu beta. And then they combine these two multiplication from different phases just into one, and the cost is same as before.
So you're assuming P1 is semi-honest?
No, it's just that we haven't got to the malicious part yet, but
Oh, okay.
yeah, here is like any party can do harm to the protocol. Yeah, I think I'll do that right now. So what can go wrong? When P1 is trying to distribute these shares, P1 may distribute some inconsistent Shamir shares. For example, some shares that cannot be reconstructed as a polynomial at all. And also when parties compute this mu gamma and they review it, their shares to P1, they could also reveal some garbage value to P1. So we need to prevent this from happening. And our idea is to use MAC and in many dishonest majority MPC protocol, the information theoretic message authentication code is used to guarantee active security or malicious security. And here, we'll define a new value called delta, which is the global key. And this will usually be secretly shared. So here in this figure, this example is not directly applied to this protocol. I just want to give an example of how delta is used to guarantee malicious security. So throughout the circuit computation, whenever computing the multiplication gates, the parties will compute two versions. One version is the true wire value, for example, V alpha, V beta, and V gamma, V nu, and wait, how to pronounce the last one? VC, or maybe it's XC. And yeah, I miss I miss working with Greek researchers. So they always compute two versions, and one is the true value, another is the authenticated version that they multiply this original value with the delta, and delta is not known by any party. So if for each gate, if there is an error from the input wires, which means that if in the input wire and the value, for example, the V gamma is not consistent with delta, not quite with V gamma, then the error would be propagated to the output wire. And then they only need to check whether for the output wire, the VC is consistent with delta multiplied with VX. Okay, so this is used in some previous MPC protocol, but so I just want to say in our setting, we also use the ITMAC, but it will be slightly different, but the idea will be the same. Okay, here is our case. So still the party will define a secret global key delta, which is the field element. It will be shared in the form as a package signature. Here I'll introduce a new notation. So this delta with a vertical bar with a subscript 1 to k, it means that it is a package signature, but only utilize one slot. For example, the first slot, the second slot, and the k slot. So the first one is a package sharing that delta is stored as the first slot evaluated at the point alpha 1. Okay. So throughout the protocol, except from having these mu's and the lambdas, and parties will also generate this authenticated version of each element in these mu's and lambdas, namely the delta multiplied with mu's and delta multiplied with lambda. But they will not be the package shares, they are only additive shares. And we thought about directly having like package shares of these values, but we didn't see any advantage of that. Okay, so and we also need a sharing transformation to go through the package sharing to additive sharing. And we'll just use the Lagrange polynomial to do polynomial interpolation and evaluation. For example, here, this L subscribed beta J and with the Fi, it means to evaluate, it is a Lagrange polynomial to evaluate from the point beta J to point alpha I. So yeah, when party Pj who holds this package sharing of F beta J, it can locally convert its share to an additive share to evaluate that point alpha I. So it's just a local computation. Each party just multiply their share with the Lagrange polynomial, then the output will be an additive share at point alpha I. So this is what we will use next. So if we have this, then for example, if we have a delta multiplied with A, which is the package sharing, they can locally just convert it into the additive shares of delta multiplied with A1 to delta multiplied with AK. So they can locally do this sharing transformation from package sharing and to the additive share. And we'll use this to get the max version of each individual Y values. Okay, here is what will happen. This is also the simplified version of the protocol. And still P1 knows these mu's, mu alpha and mu beta. And P1 is able to distribute these values in a degree k-1. And then parties will get the preprocessing from party will get this value from the preprocessing. And this includes the max version of lambda alpha, lambda beta, and also this is very similar to previous capital gamma, except that it only needs to be additive shares. We don't need to be packed share. Okay, so then they compute something that's similar as before. How to do it? Previously, there is already a packed share of the delta multiplied, evaluated as a position I. And it will multiply these three packed shares, and their degree will not exceed -1. Actually, their degree is exactly -1. And they will locally convert it into an additive share, which is the first element in that bracket. Okay. Then for the next values, they also do the same. They first compute the packed shares, then convert it to additive share. Then they get additive sharing of each individual mapped mu, which they can store locally and later use for the check. Why are we doing this? Why are we transferring all of them into additive shares because it is simple for the sharing transformation. Previously, for the computation when we do not consider malicious security, we leverage that trick of the element selection to do the network routing to get around the challenge of the SIMD circuit from SIMD circuit to a general circuit. But for the online phase, if we only keep the packet sharing shares, we don't find a very efficient way to do it if we only use packet sharing shares. So if we translate all of them into additive shares, it's just a local operation, and this max version will be additive shares for individual values. Then parties can just wherever they need to do the consistency checks, they know which element to compare with which, because they are all individuals. So this in this way, we don't need to care about the network routing for these authenticated values. Yeah, and this is everything for the protocol description. Do I also have time?
Oh, yeah, you have 5 minutes.
Okay. Yeah. And I'll mainly be comparing with this work called TurboSpeed. This is the most advanced work in the family of speed protocol. And but TurboSpeed is work in 2019, so we optimize it a little bit with some more recent techniques, and we assume that it uses a committee selection. That is to select arbitrary committee of size t+1 and do the computation. And as you can see from this table, they do not achieve constant communication for the online case. And so the SUPERPACK can get some advantage depending on the value of epsilon and n. So it doesn't always get advantage, but we'll see from this figure. So this figure represents at which point the SUPERPACK will have lower online communication than TurboSpeed. So if epsilon equals to 10%, then because there is too many corrupted parties, we can only pack very small number of secrets in a packet sharing secret. So SUPERPACK doesn't have that much advantage. So it only outperforms TurboSpeed when n is larger or equal than 34. So with the increase of the epsilon, it needs less and less number of parties for the SUPERPACK to be better. So if we fix some n's, we can also see what are the proportion of honest parties that is needed for the SUPERPACK to be better. So with the increase of number of parties, the number of honest party needed is getting less. Yeah. So, and also for the pre-processing, SUPERPACK is not always better, but generally it gets better when whenever n is large or epsilon is large. Okay. So these are some benchmark performance for the online protocol of these two, and the last two rows are for the communication ratios. These are in theory how much SUPERPACK can be better, and we use various different bandwidths to the test. So when bandwidth is large, it means that communication is not bottleneck. The computation is, but in the SUPERPACK, we do need some polynomial evaluation populations. And my intention is pretty rudimentary. And I compute Lagrange polynomial in a naive way, so we don't use FFT at all. So when network is not bottleneck, the computation is a little bit slow. So it's not very good in all the cases, but I do expect that in the future we can use FFT in the packet sharing. So, but when network gets throttled in the low bandwidth network, the communication becomes the bottleneck, then it aligns with the analysis on the communication factor. Okay, and at last, I just want to show some results on end-to-end performance. But it's not exactly the end-to-end because I didn't add the implementation of factor OE and OLE. I assume the trusted dealer will distribute these correlated values. So excluding vector LE and OLE, these are the performance for the three phases with 48 party, 1 million gates, and different proportion of honest parties. And for the vector LE and OLE, there are existing work that can generate these correlations with sublinear communication.
What is OLE?
Oh, it's oblivious linear evaluation. This let me quickly go back to. Yeah, it is used to generate this triple here.
Oh.
Yeah. So there are works that can generate this triple with sublinear communication, sublinear to the number of triples. So we also do not include them into the theoretical analysis of the.
How does this scale with the number of parties in this generation process?
For this one?
Yeah,
it does not generalize very well because I think it
Is it
needs
like n
it
squared?
needs some pairwise computations and communication.
Okay.
Yes, and also for the vector LE.
Yeah.
Also needs pairwise communication. Yeah. Go to the that's the last slide. Okay. Is there any other question?
Sorry, not theoretical, do you have this on GitHub somewhere, or is it just?
For the implementation?
Yeah.
Yeah. Right. Yeah, it's in GitHub repo. How do I send you?
I'll find you after this up.
Yeah.
Or something. It's gonna be- When you were talking about doing the FFTs, were you good? Was it a factor in both of those, like in the original sort of turbo speeds? If you, is it a fair comparison?
Oh,
You just-
they don't need. They don't need.
Yeah.
They just use digit shows. Yeah, and also, if you could notice here, actually, when the percentage of honest parties get larger, the online time is actually gets slower. This is also because the computation is not optimized, and P1 computation costs too much time because P1 has to do the interpolation. Yeah. So if we can use FFT, it might be better. So the P1 computation will be the bottleneck. Yeah, because it is supposed to be faster.
So it seems like the circuit independent preprocessing takes the longest time.
Yeah. Yeah.
I have sort of a hand wavy question, which kind of goes back to what I think Elaine was talking about before. If you do this, if you have a program that you wrote, and you take the alphas, and it's kind of a convention, you put all the alphas to the left of X. This is not, I don't think it's really material to happen over there or not. It could be anywhere. If you take just one and move it alpha 1 to be 0, plug it into your program. This is basically going to boil down to speeds in the end. If you have a delta in there and you just take K as 1 and collapse the whole thing.
Yeah, with just the one share.
Yeah.
And they said, yeah, I think in that way it might be equivalent because they just need to do a linear combination and space.
The little L's you had before, basically the L's people used before to find things. Basically.
Oh, so good.
You actually, one of the slides you had a lowercase L Lagrange interpolation.
Oh, yeah.
To decide what to add to the betas.
Right.
And if you go back to like 1979, it was Shamir secretarian, what you add in is a level polynomial.
Yeah.
Most people think of that as just adding a constant in, field element in, but you're adding a polynomial in.
Right.
So those L's actually at that point, if you just take the alpha 1 to be 0, and you're doing everything on the y-axis that you're adding, those are also the ones that tell you what to add in.
Yeah. Right.
It's not really a crypto question, but like what use case you think would have this C equals 10 to the 6 and then you do it among 48 parties? Do you think of maybe some situation where this makes sense?
I don't know, but currently the deployment, I've seen some like news, for example, in Boston area, they want to determine whether the sex is a factor when on the salary of the company workers, and they have many companies to participate in and do an MPC competition to see whether male getting higher salary than female. I think they did it in Boston. Yeah, I think in that case, I guess they do need many number of parties, but I'm not sure about if there are a lot of workers participating in, then they need large circuit.
I think this is kind of just similar to the ZK circuit, which,
Yeah, for comparison, I think SHA is like 100,000 maybe.
Yeah.
So roughly,
Cash
SHA
cow.
is like, yeah. But like the cheapest hash function is that or 30K. You can 10^6 does seem to capture some interesting applications.
but it's not very slow. I mean, 30 seconds online time is pretty acceptable.
Any other question?
One question, so like when you're generating like the circuit permutation, like the routing, how do you need, like for every multiplier, do you need to multiply it by every value in the circuits, or how does it work? Like how do you generate the routing efficiency, I guess?
In the preprocessing or from the lambda or?
Yeah, but the e's that you multiply by the lambdas, I guess.
Yeah, but for each party, the work is just to do one field element multiplication. Because they know their share on this E, right? The E1 is public, for example, for E1, it is public, and parties know the polynomial knows it's, for example, the polynomial evaluated at beta J or Pj. And Pj just multiply with that with its share of lambda. That's all that they need to do.
Oh, okay. You don't have to multiply the unit vector to all the values, because when you're doing the routing, you only. So for example, if I have this vector and then the first entry of this vector takes some value from another vector, and you know like which vector you're taking that value from. So you only multiply the unit vector, but the unit vector length is only equal to the original vector length, not the total number.
Okay.
Yeah, you just select one from this case sequence.
Okay, so let's end the recording here. Let's thanks Chenkai again for the podcast.